So in this problem, we have a 1.05 kilogram object undergoing some sort of simple harmonic motion, going back and forth, not really losing the amplitude of which it moves. We are asked, and we're given a formula here for that simple harmonic motion, negative 0.55 cosine 8 times time is, we're asked a couple of questions. We're asked, what is the amplitude? What is the frequency? What is the energy total of the system as it's oscillating? And what is the kinetic energy when we compress the spring to 0.300 meters? And what is the potential energy when we compress it to that same amount? Or when it's passing through x equals 0.3. So an important concept that you need to know is that for at any given point, the energy of the system is conserved. Okay, and it's the potential energy plus, let me erase that, I drew a K, plus kinetic energy. This is going to be handy when we get down to here. This is the one thing that you need to take from this section, is that the energy total of the system is conserved, right? As the spring reaches its maximum amplitude, it has a maximum amount of potential energy. Then it turns that into restoring force, and it turns it into kinetic energy, and it goes the other way. And then that kinetic energy gets turned back into potential energy. And it's just this constant conversion, but the overall energy remains constant. That is what we need to take from this problem to answer these questions. So when I say energy total equals potential energy over here, that is when we have max compression or extension, one of the two. It's all converted into potential energy. When kinetic energy is 0, potential energy is at its max. So using this idea, let's solve some of these problems. What is the amplitude? Well, we know the amplitude to be the absolute value here, so it's going to be 0.550. So 0.550 meters. That's going to be the amplitude. And I'm just going to go ahead and erase amplitude and shift it over so we have some space. So I'll actually write A equals 0.550. So that's the amplitude. Now, what is the frequency? These equations give you amplitude times cosine times frequency factor. So this is omega, W, or W, whichever one you want to call it, times a variable of time. We can relate frequency factor to period, and we can relate period to frequency because they're reciprocal to each other. So omega here is 8, and we're asked to find the frequency. So we're going to do a little bit of conversions, okay? We know that, let's solve for t, given, before we actually do any calculations, W equals 2 pi over t, okay? T is equal to, in this case, if we just swap their places, multiply and then divide, is going to be 2 pi over W. Okay, but we also know that period is equal to the 1 over the frequency. Okay, so I'm going to substitute t for 1 over f. Okay, 1 over f. Now, to solve for frequency, I just need to get frequency by itself. So it actually turns out that if we multiply this over both ways, we're going to get, and let me just simplify it like this, frequencies, 2 pi times frequency equals omega. All right, and this is the frequency factor which we're given here. So we can actually just go ahead and plug in. If we want to purely get frequency by itself, we just say F equals W over 2 pi. Okay? And when we plug that in, we take 8.00 divided by 2 pi. We're going to get that the frequency is roughly equal to 1.27 hertz. So we're actually going to say, we're just going to put that here, 1.27 hertz. Okay, so hopefully these two are a little bit easier. Now comes the last three questions are completely synonymous to each other, although I do recommend finding that total energy of the system. To do this, we need to be able, and remember how I said that energy total of the system equals potential energy plus kinetic energy, right? It's the combined factors that constantly are fluctuating between each other to give us the total energy of the system, assuming no energy is lost. Well, we can say, to find the overall energy, we need to get one term by itself. We don't really know one or the other. Do we know the velocity of that spring at any given point or at equilibrium? No, we don't. It's at max velocity, but we don't really know what that velocity is. Kinetic energy here is completely irrelevant if we were to compress the spring. So if I have a spring here and it's just sitting like this, and I compress it as max as it will go, aka to 0.550 meters, what is the energy there? Does it have any kinetic energy? No, it's at a maximum. As it's oscillating back and forth, if I were to let this go, when it reaches that equilibrium, it stops, and it's going to reverse direction, okay? That's max potential energy. So we can just get rid of kinetic energy here and say, okay, the energy total of the system is equal to the potential energy when we compress it to the maximum. Potential energy, in this case, is a form of elastic potential energy, and that's equal to 1/2 kx squared. Okay, so I'll just simplify our things here to say E equals 1/2 kx squared. Do we know k? No, we don't. But using this formula, I could surely find it, right? Omega is equal to the square root of k over the square root of m. Okay, I know that W, or omega here, is 8, and the square root of the mass is just, well, our mass is 1.05 kilograms. So to find k, I can just simply multiply 8 times the square root of 1.05. All right, that's going to give us 8.197. Okay, and then I can square that, right, because this would be equal to the square root of k. If I want to find k, I just take the square of both sides, and we're going to see that that is equal to 67.2. Okay, so k in this case is this, and I'm going to go ahead and erase everything but k so we can plug it into our formula. Okay, so the elastic potential energy here is going to be 1/2. K is 67.2. I'm not worried about the units here. We know that this formula will give us energy in joules, so I don't even care about putting the units. And then X is the maximum extension, which is the amplitude, 0.550 meters. But again, I'm not going to be using units here just because we know that plugging into that formula will give us joules. So 67.2 times 0.55, and then don't forget to square it. So our energy total, our maximum energy, or the energy of the system, is 10.2 joules. Okay, so we're gonna say that energy T is equal to 10.2 joules. Okay, so we found the total energy of the system. Now we need to find both energy kinetic and energy potential when we're not at the maximum, when we're at 0.300. This is when energy total is not equal to just potential energy, it's equal to also the kinetic energy. Okay, remember we had that initially, but we said when we compress it to the max, we can ignore kinetic energy. Now we can't. We're not at the maximum. It's moving slower than if it was, say, at 0 at the equilibrium position, but it's still moving and it has a lot of potential energy. Okay, what is it? What is kinetic energy? What is potential energy? I don't know. We're going to have to figure that out. Let's expand this formula. Well, we always know that this will be 10.2 joules. But what is potential energy? It's elastic potential energy. It's 1/2 kx squared. What is kinetic energy? That's going to be 1/2 mass velocity squared. Okay? So we have this simple formula here. We can actually solve for, say, kinetic energy first if we know what potential energy is. Okay, so what is the potential energy? Well, potential energy at the 0.3 meters is going to be equal to 1/2 times k. I lost my k. Oh my goodness, no, I should have kept it up there. Hold on, I'm going to rewind the footage and figure out what k is. I'll be back. I'm back. It was 67.2. 67.2. And then we need to multiply that by the distance, 0.3 squared. Okay, so the potential energy here is going to be 1/2 times 67.2 times 0.3 squared. Potential energy is thus equal to 3.02 joules. Okay, so our potential energy when we're here is and I'm just going to erase this, is 3.02 joules. Okay? Now, knowing this, we don't even have to solve for any of this stuff. We can just go ahead and say that this amount of joules is equal to 3.02 joules because we calculated that for the potential energy and we're the same amount away, that's important, plus kinetic energy. Okay, so what can we do here? We can just simply subtract over the joules to get the amount of kinetic energy in joules. So 10.2 minus 3.02 is equal to kinetic energy. So we're going to say kinetic energy is equal to 7.18 joules. Okay, that is the solution to all of these, right? So, or geez, I have these switched here. So this should be 7.18 joules. And this should be 3.02 joules. Okay, kind of a mess here with my solution, but this is all of the answers here. The amplitude is 0.550. The frequency is 1.27 hertz. The energy total of the system we calculated to be 10.2 joules. We calculated the potential energy first, being 3.02 joules, and then we found the kinetic energy was 7.18 joules. I hope you guys enjoyed this practice problem. If you did, please drop a like, subscribe, comment if you have any questions, and I hope you have a wonderful day.